Hello, welcome back to Decaf-Math, and welcome if you are new here. So today I thought that we could introduce and play around with the idea of logarithms, or just logs for short. And we often learn about logarithms in different contexts and different classes. So today we're just going to sort of build some intuition about why logarithms are useful. And then, of course, as usual, we can do some practice problems and do a little bit extra analysis. So I might as well kind of do a eeny, meeny, miny, moe and plant us right into the heart of algebra. And of course, as usual, don't worry whether you know this stuff or you don't know this stuff, or maybe you learned it long ago. Right now, it doesn't matter. I welcome you to just relax, and just let the math wash around you. Pick up on whatever you can or that you feel like, and just let the rest of it fall away. So, let's start with this equation. Something like this. X to the power of 3 equals 27. So this is an equation with one variable x, and if we were to try to solve for x, it means we are looking for a value such that when that is raised to the power of 3 or cubed, it gives me 27. So then, of course, at this point, it relies on our understanding of raising to an exponent, and in this case, it would mean what number times itself 3 times gives me 27. So what number times that number once more gives me 27. So at this point, I could just kind of guess and check. I could try 2 maybe. So 2 cubed would be 2 times 2 times 2, which would be 2 times 2 is 4, and 4 times 2 is 8. So 2 cubed is 8, so not quite 27. And I could just try values, and maybe in this case I will land on x equals 3, right? 3 times 3 is 9. 9 times 3 is indeed 27. But when we get to algebra, we slowly shift away from just guessing and checking with numbers. And instead, we want to learn some methodical, logical ways to solve for something like this. And we want to move away from guessing and checking because, well, one, sometimes the numbers aren't quite so pretty. We might not have something positive. It might not be like a counting number, right? We could have decimals and irrational numbers and stuff. So that would take forever. And two, even if we did know it was something counting, without some sort of method, it could take forever, right? So we do want something logical. So one way that we learn is that we're basically undoing whatever happens to x, because in this statement we're saying x raised to the power of 3 gives me 27. If I'm trying to solve for x itself, I want to undo that cube so I can answer, this is like a question, what to the power of 3? And my answer would say what, so that what thingy, x, is something. And so in order to solve that, I basically undo this cubed by doing a cube root. A cube root, which is written like this. Cube root. And one thing that we discover in algebra is the power of this equal sign. Whatever I do on this side, I do on this side, because these two things are literally equal. Even if they don't look equal, they are from the original statement. And so if I take the cube root of something cubed, these two kind of cancel out. They undo each other to give me x on this side. And the cube root of 27 is exactly what we were just thinking about. What number times itself 3 times gives me 27, and that would be 3. So the cube root function undoes the cubed function, and that's kind of the intuition here. If we have a variable raised to some number, the root, the nth root, kind of undoes that. And of course there are little details that we have to pay attention to when the exponent up here is even. We kind of have to consider the plus or minus case, but that's just a subtle detail. So that's sort of the intuition here, is our roots undo the situation where we have our variable raised to some number. Okay, and so that's all great and all, but how does this relate to logarithms? Well, logarithms help us deal with the situation where our variable is up on the top in the exponent. So now the question is 2 to the power of what gives me 16. So not what to the power of 3. And I should mention, don't worry too much about the like the wording, like the idea of a function. If you haven't learned that before, don't worry. We're just talking about the concept of taking the cube root and undoing a cubed. In this case, since the x is up here on the top, to solve this you might think, well, we just did the cube root to undo the cubed, so maybe we'll take the xth root on both sides to undo this x here. However, that wouldn't get us any closer if our goal is to solve for x, because you'd end up taking the xth root of 16, plus you'd have to consider all the varying cases for x, whether it's even or odd, and that doesn't get us anywhere closer to saying x equals this number, right? So that is where logarithms come in. It allows us to move this exponent down and solve for x directly. So aside from, you could kind of notice, okay, well, 16 is the power of 2. 2 times 2 is 4, times 2 a third time is 8, times 2 again is indeed 16. So you could write 16 is 2 to the power of 4, and since we have a 2 and a 2, then x would equal 4. So again, you could kind of do it by guessing and checking, or writing both sides of the equation to have the same base. However, like we said, sometimes the numbers don't work out so nicely. We can do this the same way we kind of did it here, but now we use the log function. The log function allows us to rewrite this statement in a different form. So I would write log base 2 of 16 equals x. Okay, so log, kind of like how cube root was, log itself is a function. It undoes a variable up here on the top. Log base 2 of 16 equals x. This statement is the equivalent statement to this. These two are exactly the same. And the general pattern is 2, so this base is the base of our exponent. So 2 to the power of this thing, so literally 2 to the power of, so 2 to the power of x equals 16. Okay, so it's always that 2 to the power of x equals 16. So if I had a statement log base 2 of 16, in my mind I would think 2 raised to the power of what gives me this number, and log base 2 of 16 would equal that value, in this case 4. So it's kind of this pattern, like that. Okay, so if this is the first time that you're seeing this, take your time, take your time, take your time. It does feel like a lot, and it is easy to kind of get confused with the bases of logs and stuff and how this goes. But in my opinion, you know, sometimes you might see it like log base a of x equals y, and it gets so confusing. So it might help to just write out like one particular example just to get a hang of like the pattern. So log base 2 of 16 equals 4 is 2 to the power of 4 equals 16. Like, that's the reason. So from here, you can start seeing we open a whole new world of log of base whatever. So log base 3 of 27. In my mind, I would now think 3 to the power of what number gives me 27. And in that case, it would be 3. Because 3 times 3 is 9 times another 3 is 27. Exactly. So log base 3 of 27 is 3. And you could do log base anything really. Log base pi, and there is a special case of log base e, that beautiful, beautiful Euler's number, 2.718 or something like that, dot, dot, dot. It is like pi, it's our constant, and it goes on and on and on and on and on. But if you happen to have a log with the base e, let's say a 5, you can actually, that's called the natural log, and you can also write that as ln5. So that's read as the natural log. So this is like a special case of the log function. So logo naturalo. That's not what it is, but that's how you write it. So that's the natural log of 5. And so in your mind, it would be e to the power of what gives me 5. And so since e goes on and on and on, now you can see it really is, it really isn't something to just necessarily guess and check. You could just go ahead and plug this into your calculator, because you wouldn't be able to just directly calculate this per se, right? However, there are rules. You will get an exact value for this, and there are rules for changing from base 3 to base e, or just between bases, and there are other rules for logarithms in general, but as you might imagine, since these logarithms are basically equivalent to these exponentials, it's like undoing the exponential, that our rules for logarithms are based on our rules for exponentials. So, for instance, multiplying, there's an equivalent rule for logs as for when you multiply exponents like this with the same base. So let's say 2 to the 4 times 2 to the 3. The rule is you keep that 2 and you add the exponents. So there's a log version of that. And so probably very soon we can do like a sleepy whispered video where we just write out log rules so that we can take our time and memorize those. But I didn't want to overwhelm us too much today. So just know that they exist and they all come from exponents. So when in doubt, try to rewrite whatever it is that you're doing in the form of an exponent thing. So along those lines, you can't really have like log base of negative numbers. Theoretically, it seems like it could work, but you kind of end up with ambiguous cases for the x on top, and same for 0, and same for 1. There wouldn't be like one clear answer, so you don't really have like base 0 or base 1 or base negative numbers, although it does seem like theoretically pretty cool to think about. But other than that, you could have whatever base there, and also you wouldn't take log base of anything of a negative number because no exponent would leave you with the negative here. That just doesn't ever happen with exponentials. So we can study log as a function more soon if you want to. We have y equals, that would be like log base whatever of x. And I actually got a few requests to talk about logarithms and go over logarithms, but I wasn't sure really in what context, so I wanted to start here. But we do kind of want to study the domain and the range and what the log function looks like and how the base would change the shape. But when I talk about function, in this case, it's nice and smooth. And if you put an x value, that's your input, this thing, log of whatever, would give you a corresponding y. And we know that to plot on the xy coordinate plane, we pair the x's and y's together for points, and you kind of connect the dots. So the shape just kind of in general looks very vaguely like this. But we can kind of take a look at some graphs soon. And I should also mention, I wrote it this way, but if there is no base written at all, like if there's no number there, the default is 10, base 10. So it's actually like log base 10 of whatever, like x, or 100 or something like that. So I just kind of wanted to mention the special cases just in case you've seen something similar or kind of are confused. If there's no base written, the default is 10. If it's base e, that's the natural log. And for those of you who have learned calculus or are in calculus, that's our lovely natural log. And there's a nice derivative of that function, right? So anyways, just getting used to this pattern can take a little while, so take your time with it. Just remember, any kind of log statement is, the foundation of it really is this exponential equivalent. So kind of wrap your mind around this pattern, this kind of pattern. From there, it's just a matter of learning the rules. And also, don't forget that in this case, like we said, our numbers have been nice and pretty. 2 to the power of 4 is 16. But we also need to remember, we can have fractional exponents, for instance. Let's say raising to the power of 2/3. The third part represents the cube root. And so x to the 2/3 would mean you square that number and then you take the cube root of that squared. And if you have negative exponents, for instance, so let's say 2 to the -3, the negative exponent makes it 1/2 cubed. So this is a little bit of review for our exponents and how they work. So of course all of this depends on our understanding of that. But from there, if we remember these kinds of rules, we should be good to go to solve different problems involving like fractions here and stuff like that. So we can definitely do some extra practice, but let me just give you a quick example. Let's say we have log base 2 of 1/32. So our question is then 2 to the power of what number gives me 1/32? So one place to start is to rewrite 1/32 as 2 to the power of something, because that is our question. 2 to the power of what gives me 1/32? And I may or may not recognize 32 is actually 2 to the power of 5. We actually just did 2 to the power of 4 is 16, so in this case it's 4. So 16 times another 2 would be 32. So 2 to the 5th is 32. 1 over that is actually 2 to the -5. -5, so that means 2 to the power of -5 gives me 1/32. And that actually, either you kind of line it up this way and recognize 2 to the -5 equals 1/32 by rewriting this as 2 to the -5. But there's also a log rule where if you have log base a of a to the something, a to the n, that just is n for this exact reason. So I think that's all for now. So like we said, you can use this log function, but if you just happen, let's say you're preparing for the SAT or something, and you're trying to solve something like this, logically you could also, like we said, or we mentioned, if you recognize that the 16 is 2 to the power of 4, and you have 2 to the power of what, you can just set x equal 4 in this particular case, okay, without doing logs at all if you didn't want to bother. But this is sort of the intuition behind this function. It will come in super, super handy when solving more complex equations, and it's great for studying exponentials. So I hope that this was kind of either interesting to learn or just kind of good review. These are just sort of the basics, and again we can come back to the specific rules, but before I throw all these like a's and x and y's at you, like when we did exponents and stuff, I thought that we would first kind of build some intuition about why we need them. So let me know if you have any questions, and I will see you around for more practice. And I'm kind of just jumping around still, so let me know. But for now, I hope that you are nice and relaxed, maybe even asleep. And thanks for hanging out with me, and I will talk to you soon. Bye.